Okay, welcome to the second lesson called function notation in our unit that we're dealing with, the introduction of functions. In the previous lesson we learned about what a function was and how a function is just a type of relation where for any given x value there's only one possible value that y could be. And we saw some graphs and some tables of values, and we also saw some equations that were written as functions. Well, today we're going to look at a different way of writing notations in equation form, and it's going to be called something called function notation. Well, let's think of a function like a machine, one where depending on whatever value we put in for x, we're going to get some value of y. And so we're going to think of that machine like it spits out some answer. And if we put in the same value of x every single time into this machine, it'll always spit out the same answer for y, because there's only one possible value for y. So I want you to look at this graph. This is a graph of cost on one axis here and the number of students on the other. And I want you to ask yourself, what could this graph be useful for? Well, just looking at this graph, it looks as though it doesn't quite say, what the students are for or what the cost is for. This could be for anything. Maybe they're going on a field trip, or maybe we're planning on buying textbooks and we need to know how much it costs. I don't know. But what matters here is, what can we use this for? Well, we can use this graph to be able to tell how much whatever it is that we're getting will cost if 10 students, or there's 20 students, or there's 30 students, or however many. So if I just drew maybe a dot on one of my graphs, like if I wanted to know how much would it cost for 10 students, well, I could line it up here and maybe put a dot right on my line at 10 students, and it looks as though for 10 students this thing will cost $200. And I can put a point here, the point 10, and then 200. And if I wanted to know, well, how much does it cost for 40 students? Well, I could go up here in the line, and for 40 students, well, it's above 300, so I don't know, maybe 350. So maybe for 40 students it's 350. And we see that this line does continue on forever. Well, what are some limitations that this graph has? Well, think about it. This graph has 10 students, 20 students, 30 students, or 40 students. But, well, what if I had 150 students? Or maybe even 1,500 students? It's hard for me to predict how much it will cost for that many. So then we get into the idea, well, let's create an equation. Okay, well, this seems linear, and it is linear, so how do I create an equation for this? Well, because it's linear, we get a y-intercept. Looks as though our y-intercept is right here at 150. So our equation is going to look like y equals mx plus b. Our y-intercept is right here at 150. So that's our b value. All we need now is our slope. Well, our slope is rise over run. So if I take a look at these 2 points that I've made here, I know that if I was at 10 and I moved to 40, well, the change in x there is 30. So I can say that the change in x, this little delta symbol here means change, that's 30. And we know slope is always the change in y over the change of x, or y2 minus y1 over x2 minus x1. So the change in y, well, it went from 350 to 200, or 150. So if I take those and divide them, 150 divided by 30, that gives me my slope is equal to 5. So I get this equation, y equals 5x plus 150. And this is my equation that'll work for this linear function. And how do I know it's a function? Well, I could do the vertical line test and see that only one any vertical line I put on here will only touch the function in one spot. Okay, so if I were to ask you, what is the cost if 150 students attended? Well, you would have to say, if 150 students attended, we would say that our x value would equal 150. And so we would take our equation here, y equals, and we would sub in 150 into where x goes, and then just solve. Well, 5 times 150, that's 750, and then add 150, we're at 900. So, if 150 students attended, it would cost us $900. What if 1,500 students attended? Well, we would do the same thing. We would say if 1,500 students attended, x would equal 1,500. We would substitute it in, and then we would get our answer. Now, I'm going to offer you maybe an easier way. What if I said, what does the function equal at 1,500? And I'll write it in a way that it's sort of easy to read. What does the function equal when x is at 1,500? That's interesting. That's a really easy way to read it. What does the function equal when x is 1,500? Well, we could say that the function when x is equal to 1,500 equals 5 times x, which was 1,500, plus 150. And when we multiply this out, we get 5 times 1,500 is 7,500, plus 150 is 7,650. Notice the difference between what we said here and this whole deal that we did here. This was pretty self-explanatory once I told you that when we see this letter f beside this bracket, and I set it as, what is the function when x equals 1,500? I didn't have to write a whole sentence. I just had to write this little f bracket 1,500. This is called function notation. It essentially means, what is the function at this x value? If we have this notation, now we don't need to write a sentence to explain what we want to say. And it's pretty obvious to everyone who knows how to read function notation. Oh, he's trying to figure out what the function is when the x value is 1,500. So that's function notation in a nutshell. Let's compare how we write function notation to how we previously wrote other equations. So our previous way of writing equations was what we called xy notation, where we would always write it as y equals whatever. Function notation, we write it as f bracket x equals whatever. They're very similar. What's important to understand here, though, is this f bracket x is the exact same thing as just saying y. They mean the exact same thing. You can replace the f bracket x with a y, or replace the y with an f bracket x, and it means the exact same thing. So in this instance, the writing of it doesn't make too much of a difference. But it's how we say it and how we present them that makes all the difference. For xy notation, we need to say, what is y when x equals 6? Or we have to write some sentence that says, what is the height when the ball reaches, or after 10 seconds of the ball being in the air? In function notation, all we have to do is write the function notation and everyone understands what we're trying to say. What is the function when x equals 6? Good question. We also don't say it f bracket x. The way it's actually said is f at x. Or you can even say f of x. So when you see it on the sheet and you're trying to tell me what you're trying to say, you always say f at x or you say f of x. not f bracket x. So this would read f at 6 equals, or the function at when x is 6 equals. Let's look at some examples of function notation and then see if we can solve them. Here's an example. Given g at x equals 3x minus 8, find a, b, and c. Well, the first thing you may notice is I no longer have an f at x, I have a g at x. And that's okay. It doesn't matter what letter we use as the function. It could be f, it could be g. A lot of times we'll use h for height, or we'll use p for profit, or we'll use whatever the y-axis would normally be on the graph. In our first example, we had cost, so maybe I would say c at x. And we don't even need to use x, depending on the variable that happens to be in the equation. If the variable in the equation is t, because we're talking about time, then maybe I would say g at t, or h at t, if we're trying to relate height to time. Again, the letters don't matter, it's the notation that we have to understand. So this is asking us, what is the function g when x equals, and for the first example, what is the function g when x equals 5? Again, I want us to relate this to this function machine that I talked about. We're just putting in a value of x, plugging it into this function machine, and it's spitting out our answer, our output, or what we might think of as our y value. And again, y is the same thing as just saying f at x. They mean the same thing. So when I say, what is g at 5? Replace anywhere that you see x with the number 5. If x was here and x was here, well now, in the brackets, we're saying what's the function at 5. So anywhere that I see the letter x in my equation, I'm going to replace it with a 5. 3 bracket 5 minus 8. Okay, well 3 times 5 is 15 minus 8. This equals 7. So g of 5 is 7. Okay, what about g at negative 3? Well, same idea, because negative 3 is replacing that x in the brackets. We just put a negative 3 wherever we see an x in our equation. So 3 times negative 3 minus 8. 3 times negative 3 is negative 9. Negative 9 subtract 8 more, negative 17. So our function at negative 3 is equal to negative 17. Alright, C is asking for what is the y-intercept. Don't be tricked by this. We know that the y-intercept is the same thing as saying, what is the function equal to when x equals 0? It's the same thing as saying g at 0. Well, my function when x is 0 is 3 times 0 minus 8. 3 times 0 is 0, subtract 8, and we're left to be negative 8. Let's look at example 2. Given f at x, or our function, is equal to 2x minus 5, find the value of x when f at x equals 11. So what's different for this question compared to the other previous example? Well, for the previous example, we were told what the values of x were, and we needed to figure out what the output was, or the f at x. Well, for this question, we're told what the output is. The output will be 11. We need to figure out what value of x gives us the answer, or the output of 11. So what's the input to give us the output of 11? Well, once you know how to do this, it's pretty straightforward. Because I know the output, or the answer, will be 11, all I have to do is replace this f at x, 11, where f at x was in my original equation. My output needs to end up being 11, so what value of x gives me this? So you'll see that we have x here. We probably want to isolate for it. So we'll move the 5 over to the other side. 11 plus 5 equals 2x. 11 plus 5 is 16. And so now divide by 2. And we're left with x is equal to 8. So if I inputted x equals 8 into my original function, I could say that my function at 8 is equal to 11. And we can double check that that's right. 2 times 8 is 16. 16 minus 5 is 11. Awesome. Here's example 3. Given h at x equals x squared minus 3x plus 8, can we find h at x minus 5? Instead of having a number in where x goes, now we have a variable and a number, or a binomial, x minus 5. It works the exact same way that the other examples work, though. This x just gets replaced by whatever was in the brackets here. So instead of just having an x, now it's an x minus 5. Which means that in my equation, I'm just replacing anywhere that I see x with an x minus 5. So I write my equation out. H at x minus 5 is equal to, and now anywhere I see the x, I put x minus 5. So x minus 5 all squared, that replaces that x, minus 3 times x minus 5, that replaces that x, plus 8. And so we'll expand this out and simplify our answer. X minus 5 all squared. This is a perfect square trinomial, so hopefully you remember how these multiply each other out. You could FOIL this if you need to, but I know the shortcut. It's x squared and then minus 10x. You take the two things in here, multiply them, and then multiply by 2. And then I just have plus 5 squared, which is 25. Then I distribute this negative 3, so negative 3 times x is negative 3x. Negative 3 times negative 5 is positive 15. And then I add this 8 at the end. And so when I collect all my like terms, I end up with x squared, negative 10x plus 3x. Oh, sorry, negative 10x minus 3x is negative 13x. And then 25 plus 15 is 40, plus 8 is 48. And I'm left with x squared minus 13x plus 48. That is what h at x minus 5 equals. It's not a round number, has some variables in it, and that's okay. The important thing to remember here is whenever you're using function notation, whatever is in this bracket beside our function, so in this case the x, whatever is in it, so in this case x minus 5, that replaces where x is in the equation. So anywhere you see an x, you put an x minus 5 instead. We could have used anything. We could have said, what is my function at, y plus 2? And anywhere I see an x, I'll replace it with a y plus 2. I could have said, what is my function at x squared? And anywhere that I saw an x, I would replace it with an x squared. So x squared squared would end up being x to the exponent of 4. It doesn't matter what's in the bracket, you just replace it anywhere you see the x in the original equation. So hopefully that's a good introduction to function notation, and you'll be able to finish the questions in your homework.